Thanks everyone for getting up so early, at least very early for computer scientists. Before we get started, I wanted to see whether or not anybody had any questions from yesterday. Yeah?
So I realized I'm not clear on the difference between value iteration and Bellman backup. When I did the problem set, I got the same answer doing both ways, it seemed.
Great question. The question was about sort of value iteration and the Bellman backup and what's the sort of distinction. The value iteration exactly uses the Bellman backup. So we can think of value iteration as being a procedure which for all state and actions we apply a Bellman backup, and then we repeat that process iteratively until we reach convergence. Does that answer the question? Yeah, so they're essentially equivalent. Value iteration is a procedure that uses the Bellman backup. So may I have any other questions? The other thing that I wanted to address was a question that came up at the end of last time when we were talking about stochastic approximation, which is one of the students rightly pointed out that what I proved was L2 convergence. I did not prove almost sure convergence. You would need to do an additional step in order to prove almost sure convergence. So I just wanted to make sure that that part was clear. Okay, great. So we're going to go ahead and get started. I just also wanted to make sure to give a caveat, which is this: in 5 hours, we don't unfortunately have enough time to completely comprehensively cover all of reinforcement learning, which I guess is a credit to my colleagues for doing a lot of work. So I want to be clear that we're only going to cover sort of a smattering of a combination of ideas that I think are beautiful, plus my biased opinion of what ideas are most exciting in terms of the problems that I want to solve. So just to be clear, this is not considered to be comprehensive. So what we're going to do today is we're going to talk about the control scenario. So what we were talking about before, we started off, we sort of introduced the idea of a Markov decision process, this idea of this interactive loop where we're repeatedly making decisions, receiving some signal or label about the quality of those decisions, and then trying to act in order to optimize long-term expected discounted reward. Yesterday afternoon, we talked about what happens when we don't know how the world works, which means we don't have an explicit dynamics and reward model. And we talked about doing policy evaluation in that case, meaning that someone provides us with a fixed policy. And in this setting, we're almost always assuming the policy itself is deterministic. There's a single action we would take for each state. And we talked about how we could learn that. And in particular, we talked about two sort of extremes. One was Monte Carlo estimation, which provided us with an unbiased estimator, made no Markovian assumptions. And then we talked about TD learning, temporal difference learning, which used sampling, just like Monte Carlo, and bootstrapping, where we substituted in an estimate for the value function. And I gave you some indication that this procedure was sound, but I didn't really prove it to you. Then the next thing that we're going to start talking about is, well, we don't just want to evaluate a single policy. What we really want to do is figure out ways to act in the world in order to actually achieve high reward. And so some simple properties we might like in that case is that we might like to learn what V star is. Recall that V star, I'm using star to denote the optimal value function. So this is the highest optimal value function, which we discussed is a single value function. It's unique in the discrete case. And pi star, which is the optimal policy, and this does not have to be unique. So what we're going to talk about now is how do we learn these? And then also how do we act according to these? So we would like not just to know what the right thing is to do, we'd like to take actions that achieve high reward. But it turns out that these two are separate problems. They're related, but not all of the methods and algorithms require us to act according to pi star in order to learn about V star. So in particular, let's talk about Q-learning, which is considered an off-policy learning algorithm. What does off-policy learning algorithm mean? We're going to talk about, so I'm just going to define that off-policy. So I think off-policy learning is fascinating. We'll have a lecture about that tomorrow. Off-policy learning is generally the idea of saying, how do we use the old data to compute what would happen if we acted in a different way? And Q-learning is one such algorithm, meaning that we can be following one policy and using that to estimate the value of an alternative policy. It's extremely powerful. Judea-Pearl calls our ability to do this sort of counterfactual reasoning one of the core aspects of intelligence. And Q-learning can be think of one instance of this. So what do I mean more particularly? Off-policy means that we can be learning about v pi 1 while acting using pi 2, which is not necessarily equal to pi 1. It's a very powerful idea. It allows us to do use our prior experience to learn about what might happen if we were to act in a different way. So in particular, let's write out what Q-learning does. Q-learning is going to look very similar to TD learning, but with a crucial difference that we're going to be taking a max operator. So what we're going to do is we're going to, again, right now, everything today is tabular. We have a discrete set of states and actions. Great. Yes. So we're going to start off, we're going to initialize our Q vector to something. So we could initialize these to 0, SA, for all SA. You can initialize it in different ways, and this has enormous implications for practical performance, but for convergence results, it's not going to matter. So you can initialize it to 0, and then we're going to say for t equals 0, so t is the time index indicating how we're going to act. And let's assume we start off in our initial state 0. So we're going to select an action. I'm not going to tell you how we do this, but I'm going to give you some conditions over what is sufficient for enabling us to get convergence results. So we're going to select an action in some way that we'll talk about more later for the current state for S. Let's say S is equal to S0. Okay, so we start in some state. We're going to loop for each time step. We're going to take an action. We're going to observe a reward, which is sampled from this. We don't get to know what this is, but the world gives us a reward. We see a next state S prime, which is implicitly sampled from, again, sampled. We don't know what this is. And then we're going to do our Q update. So this is going to look like our TD learning update. So Q of SA is going to be, this is an update function, so we can think of this like a line of code, is going to be equal to our previous estimate of QSA plus alpha R plus gamma Q of max over A prime of Q of S prime A prime minus Q S A. And then we're going to set S. So what's happening here, we're starting a state, we're taking an action in some way we'll talk about. We receive a reward sampled from the environment. The environment also gives us a next state. So this is from the world, from the environment, because we don't know these models. And then we do our Q update for the state and action that we were in and we took. So this looks almost identical to TD learning, except for now I have a max A here, and I have Qs instead of Vs. Yeah.
The gamma distributed across the difference.
Sorry, what?
Is that gamma distributed across the difference, or
Just here. Yeah.
Oh.
Yeah. So you can think of it as being 1 minus alpha times this Q plus alpha times R plus gamma, like a sampled version of your Bellman backup. Good question. So this is Q-learning. It's probably one of the most influential algorithms in reinforcement learning. It's very simple. I'm also going to focus on it because it's easy to extend to the function approximation setting. Okay. So now what we're going to do is think about what this does and why it works. Okay. So if we think about what we were doing yesterday with stochastic approximation, I was trying to argue to you why this sort of general procedure is sound, why this is a good thing to do. And it turns out that Q-learning is also going to converge under some conditions on alpha, which are going to imply some conditions on how we select A. So it's not going to explicitly say how we should select the A, but it's going to have conditions on alpha. And I'm going to actually change this here so that we can be a little more precise. Alpha of SA. So again, this is the learning rate. is how much we are shifting our updated estimate of the Q function. It's weighing our old estimate versus our new estimate. This is why it's called the learning rate. And I'm going to have a different learning rate here for each data in action. Or allow myself to do that. Okay, so why is this going to converge, and what sort of results does this depend on? This is very closely related to stochastic optimization. So let's go to that part first. Okay, so in very brief, doing a complete disservice to a very large community, stochastic optimization is going to be related to this problem in the sense that what we're doing here is we're doing a sampled, approximated Bellman backup. It's approximated in two ways. We are sampling a single next state, so we're sampling instead of doing a full expectation. And it's approximate because our current estimate of Q is incorrect for S prime. So I guess, and just to be clear here, so what is Q-learning trying to do, and what is our goal? What we're going to be trying to hope to show is that Q of SA is going to converge to Q star of SA. Okay. What our goal is going to be is to show that eventually this operation eventually computes a Q function that is actually the optimal Q function. So that's where we're trying to go to. Now, if we knew what Q star was, and then we were doing a backup here, it would look very much like a Bellman backup, but we only have an approximation for here, and we're only sampling S prime. Okay. So we can think of, if we think back to the Bellman equation, the Bellman equation said, let me just write it here just to remind ourselves. The Bellman equation, which we then used to derive Bellman backups, said that V star of S is equal to arg max over A R of SA plus gamma sum over S prime probability of S prime given SA of V star of S prime. That's what the Bellman equation said. And so it expressed this sort of Bellman backup, which I was sometimes calling B. So it says that the value function is such that when you apply the Bellman operator, if we think of each of these as vectors, is equal to the Bellman operator to V star. And so then if we think about the connection to stochastic optimization, it's sort of the general problem, and now I'm going to go back to my X notation of X is equal to H of X. Okay, so that should look very familiar. Over here, we said that V star is equal to the B operator, the Bellman operator, applied to V star. And stochastic optimization generally thinks about X equals H of X. And some of you guys might know more about stochastic optimization than I do, so you can correct me if I make mistakes. But I think the connection here is nice in terms of understanding some of what the theory that goes on behind why Q-learning converges. Okay, so the stochastic optimization thinks about solving this problem when H of X can't be computed directly. But what we can get access to is IID samples of M noisy observations of H of Xi plus Wi for I in 1 to M are available where this is a noise variable. So this is a noise variable with mean 0. Okay. And so stochastic optimization is going to give us some results to help us think about when we're doing this sort of approximated Bellman backup. And in particular, I'll send a link out on the webpage for a pointer to this. There's a very nice book where they go through some of the results for this case, not all of them. So I'm just going to, and they don't unfortunately prove this particular result that the next thing is going to rely on, but they go through a number of other ones that are helpful. So they're 1717 from this book, Foundations of ML, which I'll send a link out to, says the following. I'm not going to prove this one, but then we're going to prove that the Q-learning algorithm is going to satisfy the conditions of this, which is going to allow us to prove the desired statement. So that's where we're going. We're trying to prove this. What I'm going to show is that this Q-learning operator is going to end up satisfying these conditions that are going to give us the result of this theorem that is going to show that Q goes to Q star. Okay, so let's think, let H, so sort of an H like of this part, let H be a mapping, function mapping from Rn to Rn. W, T, T is in N. It's a sequence of random variables in Rn. Alpha T, T is in N, is a sequence of real numbers. And xt, T in N, is a sequence defined by, for all S in 1 to N, xt plus 1 of S is equal to xt of S plus alpha T of S. So just like what we have in Q-learning, we're going to have a state-specific learning rate. H of xt of S minus xt of S plus wt of S. Okay. For some x0, Rn, and then we're going to define a filtration. Let me switch pens. Okay, so then we're going to define a filtration ft by ft xt prime for t prime less than or equal to t, and then all of our noise variables. T prime less than or equal to t. Alpha here is going to be a vector that's defined over all the states. And it can be different, I mean, depending on how you want to write it down, it can change for each time step. So you can either think of it as a matrix, or you can think of it as a vector that's changing each time step. Okay. So F is basically just the history. It's the history of our previous noise variables and the X's and our alphas. The entire history up to T, and now we're going to assume the following conditions. Assume there exists a K1 and K2 in R, so we're just real numbers, such that the expectation of our noise variable, so Wt squared of S, given the filtration, this is just saying the expected squared variable of our noise variable is going to be bounded by K1 plus K2 according to the variable we care about, X, for some norm. So for some norm, we want to say that the noise variables, the square of the noise variables are bounded. We want to say the expectation of the noise variable with respect to F is 0. So on average, our noise variable is 0. And then we're going to make a condition on our learning rates. So for all states, bless you, in N, the sum over T equals 0 to infinity of alpha T of S is equal to infinity. This is basically saying the same conditions on our learning rate that we had yesterday, but now I'm going to index each of them by state. Okay, so the sum for a particular state, the sum over all the alphas from T equals 0 to infinity has to go to infinity, but its squared has to be less than infinity. same conditions before. And H has to be a L infinity contraction. Contraction with a particular fixed point. With fixed point. Okay, so H has to be a contraction operator with a particular point X star, which from our perspective, we're going to hope is going to end up being Q star. Okay, so if all of this holds, what the theorem says is that then we have almost sure convergence. Then, and I know this is a little bit low, then xt goes almost surely to X star. So if we're in this setting, where we have this particular H mapping, we have these noise variables, this is our operator for how we're updating, and these are these conditions, then xt is going to converge to the fixed point of the H operator. Yeah? FT is a filtration, and it's basically you can just think of it as the history of all of your previous X's and all your W's.
It's just a full list of, it's a 3 sequences?
Yes, you can think of it as just being all of basically everything you've ever seen before in this whole process. All the X's, all the W's, and all the alphas. Yeah. Mm-hmm.
Are the alphas random?
No. Well, it depends, right? It's not giving us a condition. It's saying that we're going to get to pick the alphas, but we have to pick the alphas in a way such that these conditions hold. So so in general, we get to choose those. When we're going to use this, we're going to use this in the context of Q-learning, and we're going to assume that the algorithm designer is going to pick alphas, and if they want it to or if they want to use this result to have it converge, they're going to have to pick the alphas in a way such that their sum is infinity and their squared sum is less. So for example, they could do it as 1 over the number of visits to that state action pair, and that would be sufficient. Okay. So this is theorem 17.17. They do not prove it, unfortunately, in the book, though you can find the results elsewhere, and I'm happy to point people to them if they'd like that. But this is a stochastic optimization result, and then we're going to use it to show that Q-learning satisfies this. So the way we're going to proceed to try to do that is we're essentially going to try to put our update into this format and then show that all of these results will hold. Okay? All of these conditions hold, and then therefore, if our H operator is going to a fixed point of Q star, then so will our Q-learning. Okay? So what we're going to prove now is theorem 17.18 from the same book, which says, consider a finite MDP. And then assume for all SA, all states and actions, that we have the desired condition on our alphas. Okay. So we're going to say that the sum over T equals T goes to 0 to infinity of alpha T of SA is equal to infinity. So we're going to have a learning rate for each of our state action pairs, and that their squared is less than infinity. So same conditions as what we had over there, and the same conditions we were talking about yesterday. Okay. And we're going to assume that alpha T itself for any SA is in 0 to 1. Okay. Then Q-learning converges with probability 1. And Q-learning converges to Q star with probability 1. So just to be clear here, all we're showing right now is that if this holds, then we're going to converge to Q star. It is not saying we're going to act according to Q star. But this is implying a restriction on how we're taking actions. What this is saying is that we have to try all actions in all states infinitely often, because the sum of this has to be infinite. So this is implying a condition on how we select actions. But if you could if it's possible, for example, to teleport in the environment, which it may not be, but if it is possible to teleport, or if you have a very highly mixing process, essentially you could act randomly forever, and that would be sufficient as long as you're trying all actions and all states infinitely often. Okay, so what is the proof for this? Basically, we're going to show that we can match these conditions. Okay, so proof. So we're going to let Qt of SA for t greater than or equal to 0 just to be the sequence of SA value functions computed by our algorithm. So by the definition of our Q-learning updates, we're going to have that Qt plus 1 of SA is equal to Qt of STAT plus alpha R of STAT, just the reward that was observed, plus gamma max over A prime, Qt of ST plus 1, A prime, minus Qt of STAT. Yeah.
Or with another marker?
Sure, I can try switching. Let's see. So this is just the same. This is exactly the same as over there. So that line should be okay. But I'll see if I can switch to the next one. Okay, so what we're going to do now is we're just going to rewrite this by adding and subtracting the same thing. So we're not changing the equation. But we're going to write this, and we're going to do two things. We're going to first say this is only expressing the update for a particular state in action. And now we're going to sort of think about what is the current Q value for all stated actions. And we're also going to add and subtract the same thing, which is going to allow us to write something that looks more like our kind of Bellman update. So we're going to say for all SA, is that bigger? Okay, cool. Qt plus 1 of SA is going to be equal to Qt of SA plus alpha t of SA. So notice now I'm being explicit about what my learning rates are. Of R of SA plus gamma, and this is where I'm adding and subtracting the same thing. So this is where I add and subtract the expected future sum of rewards. Okay, so this is from probability of S prime given SA. Note I don't know this, but I can add and subtract it. This is not a quantity that we observed. Qt of ut of u A prime. Okay. Minus Qt SA. Okay, I'm going to add more things to this, but what I've done here so far is I've introduced what if we actually knew what the expected discounted sum of rewards were from acting optimally from now onwards. We don't have that, but I can add that term in. And then plus alpha t SA max over A prime. This is the normal part of my Q-learning update. And then I'm going to subtract off this term. Okay. Minus the expectation over U sampled from probability of S prime given SA max A prime Qt U A prime. Can everybody see that in the back? So this looks almost the same as the Q-learning update, but what I've done is I've expressed alpha t of SA explicitly. So that's here and here. And then I've introduced gamma times the expected discounted sum of rewards and subtracted gamma times expected discounted sum of rewards. Okay. And what we're going to define alpha t SA is, so alpha t of SA is equal to 0 for a state action pair that we didn't actually just visit, if SA is not equal to STAT. Okay. Implying that we don't actually update if we weren't in that state action pair. And otherwise it's equal to, alpha t STAT. So we either let it to be some non-zero term if it actually, for a state action pair that we actually visited on this time step. So if SA here is the real state in action that we just visited, or we set it equal to 0. Okay. So now let's define, we're going to just rewrite this in vector form, and we're also going to express what W is. Okay, so WT, we're just going to be trying to move this into a form so we can apply the theorem. So WT is a vector. So it's indexed over states, where what its value is max over A prime, QT of S prime, A prime, minus the expectation. Okay. Probability of S prime given SA, max over A prime, QT of U A prime. So we can think of this as being the difference between the actual next state we saw and what its maximum value is versus what the expected next state value would be. So that's a noise term. And on average, we expect that to be 0. Yeah? No. So that should be, it's a good question. But this should be the S prime.
So what is S prime then?
That's going to be for the particular state action, next state, for the particular, thanks for asking about SAR S prime. So whenever we do this update, we're going to be applying this update for a particular state action word S prime. And for that term, we're going to define the noise term for this, like for that update for state, depends on what would be the value of your next state compared to what would be the expected value of your next state. Good clarification. Okay, so that's the noise term, and it depends on what the next state was that was actually reached. And then H is going to look like what our sort of expected, what our Bellman backup would have been. So H of QT, let's define QT. QT is a vector with components QT of SA. So we can think of what happens to QT when we do H as being defined on a particular state in action is equal to what looks like a Bellman update. Okay, plus gamma expected U sampled from probability of S prime given SA times max A prime QT U A prime. So H here looks like our Bellman backup because it has a real expectation over our previous value. So if we rewrite all of this out, then what this equation is looking like is like the following. It's saying for all SA, QT plus 1 of SA is equal to QT of SA plus alpha T of SA. Okay. Our H operator, H of QT SA minus QT of SA plus gamma times W, T of S. Okay. All right, so that's what's just re-expressing this operator in this format, which allows us to expose that it's a combination of a difference between what if we could really do a Bellman backup, what was our previous value, and what was our noise term. And so now we're ready to show that now that we have things in the form of a noise term and H, we just need to show that these things hold, these conditions hold. So this condition holds by assumption, because we've assumed this condition on the alphas. So that's the first part of the assumption. The second thing that we need to show is that our noise variables are bounded. I'll go over to, I'll erase the stochastic optimization, but I'll keep the Q-learning algorithm up. Actually, I'll do it over here just to give us a bit more space. So we're trying to show this statement right now. We're trying to show that our noise variables are bounded. I guess I'll just say briefly, this condition also immediately holds. By this definition, if you were to take an expectation over this, this would be the same. It's an expectation of an expectation. This term doesn't change. You just get an expectation in front of this term, and so that's 0. So we can show this statement holds. So the next thing we're going to try to show is this. I'll call it statement number 1. So we're going to say for all S prime in S, Wt of S is less than or equal to max A prime, Q prime, Qt of S prime, A prime, plus, just using absolute values on this expression, and triangle inequality, U of probability of S prime given SA, max over A prime, Q of U A prime, QT. So we just took the same definition of how we've defined W, and we took absolute values, and we summed things together. And this is just going to be less than or equal to 2 max over S prime. So you just pick, for any Q function, you pick the max over S prime and the max over A. Because the expected value is dominated by the max. This is an expectation over all your Q's. You take the max of that, so that's the max value. Take a max over this term, so we've got it less than or equal to 2. So this is equal to 2 our L infinity norm over Qt. And therefore, the expected value of W squared T of S, given our filtration, our history, is less than or equal to 4 Qt L infinity norm. Because all of each of these is upper bounded by this, so our variance is upper bounded by the square. I mean, our squared is upper bounded by 4. So that means that we satisfy this. They're bounded. They're bounded by something that's a function of x. For us, x is going to be q. So just in terms of the mapping, this is going to be x star, and this is x, to map between 7.17. Okay, and then the final thing we need to show is that H is a contraction. But that should look very similar to what the Bellman backup is, but I'll just write it out again just in case. So we now need to show that H is a gamma contraction for a particular norm, and what we showed it for before is for the L infinity norm. And that'll be sufficient for us to establish this final condition. And it'll look very similar but slightly different to the previous proof. So we'll have H of Q2 of XA minus H of Q1 of, well, I'm going to write it as SA. So these are just two different Q functions, and we want to show that the distance between them shrinks. From the definition of H, these are both for the same state action pair, so the rewards will cancel when we subtract. Let me just So we're going to just get gamma times the expectation over U sampled from S prime. And we're going to have a max over A prime of Q2 of U A prime minus max over A prime of Q1 of U A prime. I'll do double dots, a double, just to indicate that this could be a different action. And then we can just take the inequality in here. Move the absolute values. So now we have the expectation on the outside. S prime given SA of max A prime Q2U A prime minus max A double prime Q1 of U A double prime. Okay. And then we played the same trick that we said before, which is that if we get to separately do the max, that has to be a difference that is smaller than if we force it to use the same A prime. So the same trick as before. So this is going to be less than or equal to gamma. I'm going to do same expectation, max over A prime. Q2 of U A prime minus Q1 of U A prime. Which is just going to be less than or equal to gamma, the L infinity norm between Q2 minus Q1. Okay. So that implies that H is a contraction. It's a contraction, and its optimal fixed point is going to be Q star. So H of Q star is going to equal to Q star. So what we've showed here is that we could satisfy all of these conditions for the Q learning algorithm under some condition on the learning rates. And the learning rates imply that we have to visit all state action pairs infinitely often. And that implies that under this condition, then we're going to converge to the optimal Q star. Does anybody have any questions about that? Yeah.
You just said about how the choice of learning rates implies we have to take every action infinitely often.
In every state, yes.
Great. Where did you get that from?
Great question. So what we get is, because we're assuming that the alpha t for every individual state action pair has to sum to infinity across the learning rates, if we stop visiting a state action pair at some point, this bound would be less than infinity.
I don't understand. Those are numbers, so you can set the number to whatever you want. Are you not saying something about when you have to use that number in your Q update?
No, I'm saying that this is saying that if you sum your learning rate, so for just a particular state action pair, it's saying that if you sum what the alpha t of SA is across all time points, this is, okay, I think I understand the question. So what we're saying here is that any time that you're not in a state action pair, you have to set alpha t to be 0 for that state action pair. That's what this part of the proof is saying. Yeah, good question. So if we're not in a state action pair, when we do this update, we don't do the update for any state action pairs we weren't in. And so we define alpha t of SA equal to 0 for any state action pair we're not in. So if at some point we never visit that state action pair again, all its future alpha t values is 0. And so that would make this sum not be infinity. Yeah?
I was a bit confused by that, actually. So I thought alpha t was given to us in the theorem. Why are we setting it to be something like that?
This is so what we're doing here is we're saying that in general we think of setting alpha t for, in general when we do this update, we only do it for the state action pair we're in. What we change that to is to say, well, let's think about what this update would do for all the other state action pairs. It wouldn't actually update the other state action pairs. So at each time we're going to be in a state action pair, and we do the update of the Q value only for that state action pair. We want to be able to still define what the state action value function is for all other state action pairs, even if we're not updating them. So Q2E is still going to be defined over all state action pairs on every time step, but we just keep the same old value for those other ones. We don't do this update. Another way to think about that is to say, well, we're going to write down what this is for all state action pairs at each time step t. And we're going to do something that looks like the update, but the way we prevent it from actually changing the state action pairs is we say you have to set alpha t of SA to be 0 if you're not updating, if the state action pair is not the one that you're in and for the action you took. Does that make sense? And so we're making a constraint on how we can set alpha t SA. We're saying you can set it in any way you want, except for you can only set it to non-zero values for a state action pair if that's actually the state action pair you're updating.
So you could have put In the same statement, the thing about it being 0 when it's not a state action pair.
Right, yeah, so that's, well, I mean, this ends up being a condition on that here, but yes, it's a requirement. I mean, this is only defined for the state action pair you're in. It's just making that explicit. Because this is a condition on the Q-learning algorithm. The Q-learning algorithm only updates the state action pair for the state action you're in, and that's equivalent to setting alpha TSA to being 0 for all the other state action pairs. But what that implies is, I'm glad you brought these questions up, is that this would be less than infinity if you didn't visit a state action pair at some point. Like you never visited the state action pair again going forward. And so that's why this implies that you have to visit everything infinitely often. Which might sound like a bad idea, because that means essentially even for some actions that are really, really bad, that you're going to have to still try them infinitely often. Yeah?
So that means that if in the algorithm you stop updating a particular state action pair, then you will never convert to the optimal state value function, right?
Well, no, it doesn't necessarily say that. It says that in order to, this proof says that in order for it to definitely converge, you require that. It does not, it's not bidirectional. Yeah. You might still converge and it might be fine. And in practice, you almost never do this because you don't want to continue to take really bad actions forever. But this is just saying that this is a sufficient condition for convergence to the optimal. Okay. And the interesting thing about this, to me, is that is still a pretty flexible general specification for how we have to act. So it's not saying that we ever have to follow pi star. It's just saying that you have to try all actions infinitely often in every state. And so there could be many, many ways to try all actions infinitely often in the states, and you would still converge to Q star. And that's why it's an off-policy learning algorithm, is because as long as you're acting according to something that would give you these conditions, then you're still going to converge to Q star. That is not always the case. So in some other algorithms, it's more important to start to act according to the optimal policy. In particular, for Monte Carlo algorithms, Monte Carlo algorithms are just averaging over your expected returns. And so if you are not ever acting optimally, as you might expect, those averages aren't going to converge to the optimal policy. So this is a looser requirement to guarantee that you converge to optimal than like a Monte Carlo algorithm would require. Okay, so this answers the question that I had raised before, which said, how can we be sure that we're going to guarantee that as we act in the world, we're going to converge to the optimal value function? Another thing you might want to know is how can we make these decisions in a way such that we will both converge to Q star and will eventually act according to Q star? And a very simple condition for this is greedy in the limit of infinite exploration. So I'll just write that out. Is everyone done with this part? So what this is going to allow us to do is to ensure that asymptotically we're going to be acting using all the information we gained and be making good decisions. And it is a simple approach to acting. And what we'll start talking about this afternoon is much better ways to leverage the information that we have in order to get better performance faster. And that'll also allow us to start talking about how do we compare different reinforcement learning algorithms in terms of their performance. Okay, so the question that we want to answer here is, how can we eventually get to using pi star? And why do we want to do this? Well, that means that we're actually acting optimally, which means we're gathering the most amount of reward we could hope to get. And that seems preferable because that's sort of the goal of reinforcement learning. So greedy in the limit of infinite exploration is sufficient for this. Greedy in the limit of infinite exploration, often called glee. And all this says is it says NSA I, where this is the counts of visits to SA at time step I. So if we think of how many times we visited each state action pair at time step I, what we want to say is the limit as I goes to infinity. This has to go to infinity. We're visiting all state action pairs infinitely often, which was also implied by this condition. And the second condition we have to say is that our behavior policy, how we're actually making decisions, we can think of this as our behavior policy. I'll call it pi. Our behavior policy, how we're making decisions, has to converge to the greedy policy with respect to our Q value estimate. So the behavior policy converges to greedy. Okay, so limit as I goes to infinity of pi of A S. I'll index this by I because that's the policy that we're using to make decisions on the ith step, has to be equal to argmax A of Q of SA. Okay, so as we go to infinity, we have to be converging towards exploiting the information that we have in our Q function. And the reason that's a good idea is because our Q function is itself converging to Q star. So given that Q is converging to Q star, then taking argmax with respect to that is really giving us pi star. And so what this is saying is that as t goes to infinity, then the way we're acting has to be to follow pi star. And a simple condition for this is to do E greedy. So E greedy, which is with probability 1 minus epsilon, pi I of A given S is equal to argmax. So with some probability, you exploit your current knowledge using your current estimate. And with probability epsilon, you select A randomly. So with some of the time, you just act totally randomly. You gather data. Essentially, you explore. And with probability 1 minus epsilon, you exploit your current estimate of what's a good thing to do. And an E greedy is glee with some conditions on epsilon. Sufficient condition for this to be glee. If EI is equal to 1 over I. So we decay our epsilon over time. So this is really simple. This is used extensively, particularly in a lot of deep reinforcement learning. It doesn't always work. It works shockingly well a lot of the time if you can do careful tuning of epsilon. The challenge is that often you don't know how to do this. If you're doing games, or if you can repeatedly play with the environment a lot of times, it's often quite reasonable to figure out what are good strategies for this, treating this as a hyperparameter optimization problem. But in problems where, like customer management or patients, et cetera, then often we would have no idea of how to set this. And this generally would do a lot of exploration. You're going to continue to have to take all actions in all states for a very long time. And this is taking A randomly, right? So some of those actions might be really, really bad. But this is a sufficient condition, and this sort of starts to introduce the ideas we'll talk about this afternoon in terms of exploration. Now, in our remaining 6 minutes, I want to really briefly say how we can extend all of this to the function approximation case. So note that in this case, we have this Bellman backup, or this sort of sampled, approximated Bellman backup. And we can do it exactly in the sense that this is just, we can think of this as a matrix or a series of vectors, but we can perfectly represent the Q function given the data that we have so far. The problem, as some people brought up yesterday, is that if the state and action space is infinite or just extremely large, this is still going to be prohibitive to keep in memory. And it's not going to be tractable to visit all states and actions infinitely number of times. And so we're going to need to do some sort of function approximation in order to represent this. And so the key idea of things like fitted Q iteration is to treat this as a regression problem. Okay, so essentially in those cases, we're simply going to parameterize Q. This could be with a deep neural network. This could be with a linear value function approximator. Let me just quickly write that up. And so that allows us to use a lot of supervised learning techniques in order to do this fitting. Now, while I'm erasing this, I want to highlight something else, which is how many times are we using a state action reward S prime pair in order to update our Q function? Like, I get a data point, which is SAR S prime. I use it to update my Q function, and then what happens to it? Do I ever use it again? If I don't experience that state action reward next state again? I think I heard somebody say it.
No.
Nope. Right. Okay, and does anybody think that might be a problem? Well, it's great in terms of computational efficiency because this update doesn't depend on the size of our state space. This is a constant. It requires us to do a max over A, so it's going to be an order A operation, but this is totally independent of the size of our state space, so that's nice. The downside is it's super data inefficient. And a nice example for seeing this is if you think about something like a chain MDP, which are often used for sample complexity results or illustrations. So if you have an MDP which looks something like this, where you have to kind of go to a really long train, and you get like a +1 at the end, like maybe you're playing Go or some other game where you only get a reward if you do all the right actions till the end, then Q-learning can be really slow to do updates because when you get this information, you only update the immediate previous state in action. You don't keep that data around. And so one thing that's often helpful to do is to do this essentially kind of sampled backup repeatedly with the same data. And that can allow you to propagate information backwards. And so it can be much better in terms of data efficiency. So in fitted Q iteration, we can think of this as sort of helps briefly kind of sketch the idea. We can think of doing something very similar to this approach, but with function approximation and being able to reuse our data. Let me do. Okay, so what's the main idea is that we can think of what Q-learning is doing right now is we're getting a series of state, action, reward, S prime tuples. Like we're gathering those over time, and we can think of just storing these. So on each time step, we have a state, action, reward, S prime tuple. And we can write these down as trying to sort of construct a new data set that we could then use supervised learning on. So in particular, we can think of saying, let's construct a yi, which is going to look essentially like this equation. Yi, so this is for, you can think of this as being for a whole bunch of data. So over n time steps, I'm going to have n tuples. So let's say that I'm going to try to turn this into a supervised learning problem so that I can use function approximation. I want to write down Q as being equal to some function of some parameters. And I'm going to do that so that I can do generalization if the state space is really large. So if I do that, I want to figure out some way to fit that function. And one way to fit it is to say, well, I'm going to define yi to be equal to ri plus gamma max over a prime Q from, I'll call this, I'm going to index this by iteration so that you can think of this as your previous estimate of S prime. SI. Okay, so this is indexing. For this particular tuple, I'm going to do an estimate of what the Q function is, okay, which is going to be an approximate Bellman backup, right? Very approximate, right? But this is like from SI. So we could create all of these tuples, which is a little bit like taking each of these and then using them to create some target estimate of what the Q function is. And then once I have it, I just have all of these SIAI YI pairs, so I think of it as like this. And now this is a supervised learning problem. So I can try to fit QK, which is going to be parameterized right, to minimize a loss between on this data set. So I'm going to fit a Q such that I can try to accurately predict YI for each SIAI pair. And then we can throw that at deep learning or linear regression or a number of different techniques. And the reason, I know there wasn't enough time to really go through this carefully, but I wanted to highlight this because for Q learning, the major innovations over the last 5 years, at least a large number of them have been thinking about if we want to deal with infinite state spaces and sometimes infinite action spaces, then we need some way to do generalization and approximate this. One way to do that is to parameterize our Q function, and then we can use sort of similar types of ideas to then apply supervised learning to fit our function, given the data that we have. And then once we have that function, we can still use it to act and select actions, but now we're just using a parameterized function. And so there's been a very large body of papers on this. I just want to highlight there's a number of challenges that come up to this, and I think one of the reasons why we didn't see a lot of progress on using deep neural networks for reinforcement learning for around a decade, maybe even 15 years, is that there's some well-known lack of convergence results once you start to introduce function approximation. So we proved here before that Q learning is going to converge in the tabular setting for finite state interactions. As soon as we introduce function approximation, that is not always the case. We have to use additional assumptions. There was some important results from the 1990s from people like John Tsitsiklis and Ben Van Roy that prove that with things, even simple regressors like linear regression, that this wouldn't necessarily converge. And so I think for a long time the field thought, well, if in even simple cases, this might be a non-stable approach to trying to compute Q, like not even saying how good is the point you converge to, just no convergence at all, that people didn't pursue function approximation plus Q learning type techniques for a while. And then people realized that in practice, it often does pretty well. It may or may not converge, but it can still get you a Q function that's pretty good for acting, and in particular, doing really well at Atari and a lot of other things. But in terms of convergence results, this introduces a lot of subtleties when we combine with function approximation. And there are results for these type of algorithms that also have implications for some of the stuff we talk about tomorrow. But it's still a very open area to figure out strong results for that setting. So what we'll do now is that we've sort of talked about a very simple way to try to select actions, which is GLEE, sort of this like just act randomly or follow the what we think is optimal right now. And this afternoon, we'll talk about smarter ways to do exploration. Thanks.